So when do you want to do that?
When they do it the business meeting.
We don't have too many people here.
You drive by, but I get up to
Yeah.
It's completely off topic, but we need this for the clinic. So do you want to take it or should I take it?
I mean, I should be there, but yeah, maybe it's better if you take it.
Okay.
All right, so this computer, well, actually, technically, they both have, I think, video running right now. All right, so that's muted.
Complexity, huh? And where's the clicker?
And we joined the club. So we'll run off this computer and Dave's will switch over to his. Nothing is just running anything. These are keynotes. It's happening fancy. You were 13.
I turned 17.
We had to buy, like, oh, finally, here, iPod. It's not our thing, so we had to help them. But best parents. Yeah, then everyone has one, but like.
Best day of my life.
So she just goes out in the backyard, you can leave it plugged in, and then she goes in her room. Like, yeah, all night telling you what you want to do.
Without freezing.
Which was actually, I mean, we did it as like, not lazy, but well, sort of, but his parents who couldn't be hassled to figure out how to use the telescope.
And the daughter who couldn't figure it out.
Yeah.
That's the guy shopping.
So exciting.
Find out the second one. See if I can find out.
And I learned by force about
Is there anyone to man the light switch?
No.
Or
would you
woman
like?
the light switch? Yeah.
I would love to have you do that. Thank you.
Well, I don't know what they do, so I'll have to play with it.
That's okay. Playing is fine.
pay is not very good.
David, did Jeremy explain to you about standing so the camera can see you?
No, you did not.
Okay, so you kind of have to be like in front of this camera, yeah.
Okay,
So
great.
you can talk to the audience, but
Awesome.
this is where the camera will be.
Okay, that sounds good. I'll turn this around so I can reach my buttons. Please. See what I'm doing. All right.
Clicker too.
What's that?
It's connected to my computer.
But we have a clicker, but I guess you're gonna switch it over.
Yeah, we could.
We could switch it.
It's all good. I'm happy with just
Okay.
tapping it too.
Okay.
And then I brought my other pointers.
Okay. Alrighty, looks like I better start. Hello, everyone. Could you take your seat, please? We're about ready to get the meeting started, so if you could have a seat, I'd appreciate it. Sure. Are they both on or is?
Yeah, it's both computers.
But this is, it's showing this view, it's not this view.
Whichever one is active, yes, we could shut off the display. Then we shut off the camera from here. That's right, it should be fine. Most of what you can see is the screen anyway. Yeah.
Good evening, everybody, and welcome to the May meeting of the Delaware Valley Amateur Astronomers. My name is Jan Rush. I'm the president of the club, and I'm very happy to have you all here tonight. Wanted to start, actually, could we have the lights down, please? With this great photo by Mark Diorio of the Rosette Nebula, Caldwell 49. And what's especially fun about this is that it was taken at Valley Forge during one of our star parties. I don't think you thought we could see something like that at a star party, but of course it was taken with a Dwarf 3 smart camera. But I think it's a great way to emphasize what a great event that is. And here we have a very special view of the Mercurian chain. This is a photo that was taken by Daniel Adibi, one of the members of our club, and he's a high schooler. You might remember that last year he had won second place in the Astronomical League's Herkimer Parker Youth Imaging Competition, and he won again with this gorgeous image. And it was the astronomy picture of the day, which is a great honor. It was the astronomy picture of the day on April 17th. So thanks to Dan. Amazing. Now, what are we looking at? We're looking at Markarian's chain, and this is a lovely chain of galaxies that anyone who's worked on the Messier objects will recognize. There are two Messier objects in the chain, M86 and M86 and M84. This one's pretty famous, M87. That's where the black hole is that was first imaged a couple of years ago. And of course, we have these two fun interacting galaxies, Markarian's eyes. So thanks to Daniel for a great image and a great honor for our club to be in that situation of having someone win the Astronomical League Award for imaging. We're also honored that another member of DVAA, Dan Stern, also had a picture of the astronomy picture of the day on April 24th. This is an emission nebula in the southern constellation Norma, known as the Dragon Egg Nebula, NGC 6164. The central star, central star here is a very young star, and the surrounding gas was ejected from this star. And you might say, well, why is it called a dragon's egg? Why not a dinosaur egg or something else? Well, it's because it's very close to what's known as the Fighting Dragons of Ara, NGC 6188. And if ever a nebula looked like its name, I'd say this sure does. So this is something fun that's happening right now. I don't know if anybody's taken a peek at Saturn lately, but the rings are disappearing. Not really, of course, but this is a nice view of the way Saturn looked between 2020 and 2025. And on March 23rd, we had what's known as a ring plane crossing, where the edge-on view of Saturn's rings makes it look like this, and they seem to disappear. Occurs about every 15 years. And why is this? Well, because the rings are very thin and flat. And as Saturn orbits the sun, its rings can align edge on with Earth, making them appear to vanish. Now, there's only about another week you can see this in the eastern sky before sunrise, but then it'll be visible again in late August through the end of 2025. This was something that really confused Galileo, because he couldn't really see Saturn's rings. He called them ears, but he could see that Saturn wasn't actually round. And when they disappeared, he had no idea what was happening. So you have a chance to also experience that phenomenon this year. Okay, coming back to the present day, these are some of the upcoming events. We have a clinic, a dark sky observing clinic for members, which is happening next weekend. We are filled up right now. We have a great group of people and a fantastic group of experts that will be helping you. And we're just hoping for good weather for that. If you are sorry, if you missed signing up and you wanted to sign up, put your name on the wait list and we'll know how many people are interested. And we'll try to offer another clinic this year if we have a lot of people that sign up on the wait list. On May 31st, we have the Radnor Great American Campout. And that's being led by Barry Johnson. He says he's got some volunteers, but I guess a few more would be welcome. All the information is on the website about that one. June 7th, we have the Public Star Party at Valley Forge National Historical Park. June 11th, our workshop, astrophotography workshop. And June 13th is the monthly meeting here in this room. Also wanted to mention the Friday night lights at Cheslin Preserve, and I'll have a little bigger piece on that. And also in June is the York County Star Party. Many members of our club have gone to this star party. It's a fun little star party. So check out the information on the website because you might be interested in going. It's an overnight star party, not too far from home. Friendly group of people in Susquehannock State Park, which is dark. Now, Friday Night Lights is a fundraiser. There's local craft beer and wine, food trucks, music, and astronomy. And if you are one of the astronomers who sets up at this, you'll get in for free along with 2 guests. It's a fundraiser for Natural Lands, and what you need to do, one thing is nice is it's multiple clubs participating. So if you've ever wanted to meet people from other clubs, this is a nice opportunity to do it. The person organizing it is Fred DeLucia, and you need to contact him if you'd like to come. He'll get you your name tag and your free passes.
How much is the ticket?
Well, they're free for the astronomers. I think they're $30, something like that per person. If you're not an astronomer. And I put this slide in here before I knew we were full. But we do have a dark sky telescope clinic for beginning and intermediate observers coming up this weekend. And join the wait list if you'd like to go to the next one. So I have an announcement on someone who's taking over on the door prizes. This is Joe Kraus. I think many of you met him. I don't think I saw him here today. No. Okay. Joe Kraus is going to be manning the raffle table. And if you have anything to donate, you can either give it to Joe or give it to me or one of the other officers. He's taking over because Ken Keplinger is now the outreach chair, so we had to share the work. And also, as many of you know, we lost Lou Varvarizes, the chair of the astrophotography committee. But we're happy to announce that Gary Trapezzano is going to take over as the new chair. Want to raise your hand, Gary? So everybody knows who you are. Now, Gary knows everything there is to know about all the latest astrophotography tools, and that's why I thought this picture was good, because he's showing you one of the most modern tools that he will be utilizing during the workshop. And wow, lightning strikes twice. I'm really excited to announce that we again won the Mabel Stearns Newsletter Award, first place award, from the Astronomical League. And this edition that we submitted was, the lead editor was Ken Keplinger. So let's give Ken a huge round of applause. I was very surprised about this. I didn't think it would happen to us twice, but this is great.
Jan, does that mean that, Doc Allen, is it Allen?
Uh-huh.
We'll have to make, another trek?
Well, what they do is they invite Ken to visit the Astrocon, which is in the annual convention, which is in Bryce Canyon this time.
Yeah.
And if it's not, if he can't make the trip, then they mail it to him. But, yeah, that's the usual procedure. What last year was a special thing. What we learned though is that once you win the award, you're ineligible for 10 years. So, not the club, but the editor. So Ken is now ineligible. Tom, who won last year, is ineligible, so.
We got 4 more.
We got 4 more people, right?
How many do we have to win before we become the New England Patriots? Astronomy newsletters.
We might be counting our chickens there. Okay, so reports. Brian unfortunately is ill today, so he asked me to announce the new members. We have 5 new members. Stefan Lesher, Andy Lesher, Sophia Lesher, Wayne Brown, and Harvey Bass. Are any of them here tonight? Okey doke, well, welcome. And do we have anybody here who's new for the first time? Who hasn't been here? Ben. Scott, maybe you could turn the lights on now? Thanks, so we can see poor Ben. All right, welcome, Ben. Thanks. Have say hello to him after the meeting so that you can meet him. Okay, now we have a very special report from our VP Tom Nolasco, who's going to update us on DVAA merchandise.
Hello, I'm Tom Nolasco. And we've been fooling around with the idea of merch for a while. Oh, I get on the camera. And we finally got around to doing it. So here's an example. This is a polo shirt that we're having made. It's Delaware Valley Amateur Astronomers on it. It's embroidered. It'll come in the different things. I'll show you a few examples of different things we're doing. The merch we're going to provide or make available for sale. Basically we'll have these in several colors. I don't know, somewhere between 4 and 6 colors each item. So this is the polo shirt. It's like a 65-35 polyester to cotton type of thing. And then we have the t-shirts. Now we decided to go with, it's called direct to film versus screening. Saves us the screening cost setup. And also as you have, we have the color stars in there. We got a yellow, red, blue, and orange star. Kind of matches the original. Don McLaren has several old shirts, and I saw his, and it really got me thinking that's really a nice way to go. So anyway, it's what it looks like in gray. With the direct to film, they say you should watch the high heat. Now I got a bunch of direct to film shirts at home, and my wife just turns them inside out when she puts them in the dryer, and that seems to preserve them for years. So anyway, we have that. We have got a version here in blue. I'm gonna leave these all up here so you can look at them after the meeting. Basically the same thing in a royal blue style. We have a sweatshirt style. This is a forest green, I think. It's about a sweatshirt. These are all embroidered, except for the t-shirts. Everything else is embroidered. This shirt, sweatshirts, and everything else. Now, I didn't, it's usually just samples. I didn't, get a hoodie made. We're gonna have hoodies available. We're gonna have a zipper hoodie available. It's a little more money for the, for the zipper. I'll smile. But so that's what a sweatshirt looks like. And then we have hats. We have a solid hat. That's all one, an adjustable band, one size fits all. We have a two-tone baseball cap available. And wait, there's more. We have we're gonna have beanies too. And surprisingly, I'm very impressed that they could embroider this so nicely on such a soft material, but did a great job. So here's a one size fits all too.
Is it a make astronomy great again hat?
Something like that. Make Denver Valley great again. And the final prices really haven't been agreed upon yet per se. We're close. And give you some estimates. Basically, in all these, the hats are just one price for everything. The hats are like ball caps are probably going to be about $22 for one of these, roughly. Doesn't matter if it's solid or two-tone. Beanies are about $18 sale price. The sweatshirts are going to be about, now in these shirts and sweatshirts and things like that, from small to extra large is all the same price. Once you get into 2XL and 3XL, they charge you more because there's more material, I guess. So sweatshirts are going to be in the ballpark of $28 for small to extra large, and then like goes to like $30 and $33 for like 3XL. The polo shirts are going to be about $32 for small to extra large, and then 35 and 38, that kind of ballpark. And the t-shirts are going to be in the ballpark of $18 for small to extra large, and then 24 and 27 for the other two sizes. So, pardon me? Oh, the zipper, yeah, the hoodie with the zipper. That's cool. The hoodies, I can give the hoodie price, did I? The hoodie, the sweatshirt, like I said, was $28, $30, $33. The hoodie, no zipper, is like $38 small to extra large, and about 46 jumpsuit for 2XL, 49 for 3XL. Hoodie with the zipper starts at 48 for the small to extra large, 52 2XL, 55 3XL. So that's the ballpark where things will be. They'll tweak a little bit. I don't think they'll go up. They might tweak down, but they might not either. So anyway, I'm gonna leave this stuff. I'm gonna put it on the top of the shelf here, and you guys can look at it after the meeting and see what you like. And we hope to have, I especially hope to have a storefront available on the website. And the basic plan of action is we will put up on the website. You will select the items you want. We'll have a sort of storefront. It'll just be a button. It'll be there for a month, say. And you click on it and you can choose what kind of, like a men's or women's t-shirt, men's or women's polo shirt, sweatshirts and all are just are unisex, I guess, and the hoodies and stuff. But anyway, we'll have the everything up there. We'll have the prices up there. You select it and you add to the cart just like you would anything else for an online purchase. You pay for it there. So all the money is handled through the Club Express website, our website through Club Express, and that's all good. Now, this is the fun part for me. I'll take when we close it down, I look at all the orders, come up with a simplified spreadsheet of exactly what was ordered to take to the store. And I'll give it to them and go, okay, here's what we're going to order. And then I'll pick it up probably about 2 weeks later. It took about 12 days to get these made from the day I handed it to them. And so say 2 weeks, and I'll get a box of stuff. And way it's going, I'm not going to ship anything. You're going to pick it up at the meeting here or at Valley Forge. I'll bring it to both places. And like I was telling Jan, probably for the rest of my life, I will be carrying at least something in a box back and forth year after year. We didn't pick it up. But we'll give it a try and we'll see how it works out. If it works out pretty well, we'll probably instigate it again, maybe in 6 months. We'll put it back up. Someone wants to buy something, some new members, we'll put it back up. So anyway, that's the game plan. So we'll see how it goes. Hopefully I'll get when the website comes up, I think we should probably blast a general mailing to everybody. Send an email to everybody saying, go to the website, send the merch, and I'll try to have some pictures of the stuff on the website too, so you can kind of see it and with the colors and things like that, so to kind of make your purchase a little easier. Anyway, that's the story.
Thank you so much, Tom, for doing all that. There were multiple steps to this process, as you can tell. It started with taking the logo and working with it to get it in shape to be able to embroider it like this. So Tom did a lot of work on it, and I think the products are going to be great. Okay. Anybody else have any reports or announcements? Martin?
Oh.
Go ahead.
I'm looking for one or two additional fellow wizards to help on Friday, the Kennedy here. To help with the Heinz Nature Center Star Party, which was rescheduled from last Friday. We had about 40 there last year. They're expecting 100 or more this year because it's being done in conjunction with another activity. So I have a few volunteers, friends of mine that are going to help, but we could use one or two with or without telescopes. And we'll post it on the website now that I have it confirmed. And
What's the date?
It's Friday, the 23rd. There's no rain date.
Of May.
Yeah, 2 weeks from today. And and the contact information for me or Ken Couplinger is also involved in it. So if you can help, really, we only need maybe one or two people at the most. So, and a few of you were there last year, so you'll remember what it was like. And that's it. Thank you.
And it's
At the Heinz Nature Center, that's out near the airport.
great, thank you. Jeremy?
Yeah, just a short announcement. As you know, Lou Barbarese has passed away last month, and a number of you were able to attend the funeral. Last night, I had the opportunity to visit with Lou's parents and his sister Alexandra. They're going to be doing a memorial service for him as well through their church. And that's actually going to be next Sunday, the 18th. So it's mostly going to be family attending this, but they did say that there are some openings for DVAA members who'd like to show up. So that will be the service on Sunday morning at St. George's Greek Orthodox Church. I think that's in Upper Darby. And then that'll be followed by a luncheon at the Drexelbrook. So if you're interested in attending that, let me know, because they need to get a list of the people who are coming, because they have kind of a limited number of openings. They said maybe up to about a dozen. So if you're interested in going to that next Sunday, just let me know tonight, and I'll get a list of names and I'll pass that along to Lou's sister.
Thank you. Okay, the time has now come for our observing report. Sylvie Summers up next to update on Corona Borealis.
Thank you. Perfect.
Just turn this on your pocket.
Okay, which one is, oh, perfect. Where's the clicker? Thank you. Hello?
Let me just get the screen shared.
Oh, okay. Which button does?
So this is. There's.
All right, is it ready?
Yes.
Oh, hello. My name is Sylvie Stomberg. I am the junior board member at large at DVAA, and I'm going to be presenting on what's going on with T. Corona Borealis. Now, as some of you would know, as some of you would know, on April 26th, oh, wait. Help.
Working.
Okay.
That should be good. Try the button. Now try the button.
Thank you so much. Now, as some of you would know, on April 26th, 2024, I gave an observing talk about T. Caroni Borealis, the flare star, predicting that it would flare and erupt on September of that year. So on the next slide, just to do a recap, because a lot has happened since then, I'm going to be detailing everything that's happened with the star system in just over a year since I last spoke. Are you ready? Because this is going to be quite a bit. No, that's not a technical difficulty. Absolutely nothing has happened with the star system since we last spoke. We thought that the star system was going to erupt in September of last year, at the start of the school year, and now it's exam season, as many parents in the audience are tired of hearing. So, what happened with the system, and why hasn't it flared yet? Well, before we look into the future, we're going to do a quick recap of what T. Caroni Borealis is for those who'd like a refresher after so long, or those who didn't see the last presentation. So, T. Caroni Borealis is a nova star. It's a binary system composed of two stars that orbit each other around a common center of mass. So, the first star is a red giant in T. Caroni Borealis specifically. That is a very old star that has exhausted the hydrogen in its core and now burns helium. And what's orbiting it is the leftover core of a dead star, a white dwarf. Now, this white dwarf is far more dense than its living companion. So therefore, this white dwarf draws mass from said companion into an accretion disk. Think of it a bit like when you hold up an hourglass and all the sand from the top starts trickling into the bottom. That's a bit like how the white dwarf takes mass from the red giant. But then eventually the white dwarf is going to create an atmosphere around itself. And since the white dwarf is very hot and very dense, that'll eventually reach a critical heat and a critical mass. And when that happens, the star is going to expel its atmosphere into space in the nova that's going to make it extremely bright. 1,500 times brighter. Show of hands in the audience. How many of you have had an observation of yours spoiled because of the brightness of a full moon interrupting? Perfect. Another show of hands. How many have had your observation interrupted by the brightness of Venus interrupting? No hands, as I anticipated. Now imagine if something the brightness of Venus became as bright as a full moon in just a couple of minutes. That is how bright T. Caroni Borealis is, or a star that's barely visible going to the brightness of the North Star, which is exactly what's going to happen. Now, to explain the flare in slightly more familiar terms, I'm going to compare it to a balloon. Don't worry, I'm not going to be popping it today. So, a bit like a balloon. Well, imagine that this is like the atmosphere. And as the atmosphere fills up with more and more and more air, it'll eventually hit a critical mass where it can't carry any more and violently burst, which I won't be doing to you today. Now, for nova stars, we can imagine that once one balloon pops, another balloon is going to appear and fill and fill and fill. But why hasn't T. Caroni Borealis done this yet? Like so many things, we don't know when. In all honesty, trying to predict when T. Caroni Borealis is going to flare up is a bit like trying to predict when there's going to be smoke pouring from the chimney at the recent conclave. It's impossible to know when it's going to happen, but there are signs that let you predict when it's going to happen, which is exactly how NASA got this wrong. Now, T. Caroni Borealis is being looked at constantly by astronomers, so NASA was measuring it, and they noticed something that made them pull a massive code red false alarm back last year, which is why they said it was going to erupt, but it didn't. Now, what we're looking at here are two different light curves. On the left, we can see a light curve for T. Caroni Borealis from the years 2021 to 2023. And on the right, we can see when it last erupted. And on both of these, we can see green and blue dots. And I'll explain the difference between them. The green is light taken through a visible or a yellow lens, and the blue is taken through a blue lens. this is mainly just so that astronomers can figure out more about the star, and we don't need to discuss it tonight. But as we can see, just before the eruption in 1946, and just before the eruption, well, that didn't happen, we can see a little dip right here in the brightness. And the reason that these stars have a dip in brightness before they expel their atmospheres is because all of the accumulated mass is going to dim the light that reaches us from the star. So, as we can see here, NASA saw a dust dip very similar to the one before the previous nova and pulled a code red, believing that that meant it was going to go off, but unfortunately, this did not happen. So, that begs the question we've all been asking for quite a long time now. Where do you find T. Coronii Borealis when it does blow, and when will it blow? My prediction is that it could go off this year, but I should make it very important to say, do not take my word for this. But when it finally happens, or at this point, should I say, if it finally happens, you don't actually look for the star T. Coronii Borealis first. What you should do is look for the bright red star Arcturus in the constellation of Boötes, which is known for its bright red hue and very noticeable luminosity. Then from there, you'll want to look for Corona Borealis, which is about between Arcturus and the other bright star, Vega, known as the brightest point in the summer triangle. From there, you'll see two stars of around equal brightness in Corona Borealis, one being Alphecca or Alpha Coronii Borealis, and of course, T. Coronii Borealis when it finally blows. Or, if you have equipment, or you're a bit lazy like I am, the coordinates are right here if anyone would like to see those. And in conclusion, that's the situation with T. Coronii Borealis, and let's hope for clear skies and that I won't be back in 2026 for a third time. Thank you. Any questions, or are there any questions, or?
Are we starting an over-under pool? Club?
That would be fun. Well, that's it. Thank you guys so much.
Thank you, Sylvie. That was absolutely great. Okay, it's time now to turn the meeting over to Jeremy Carlo, our programs chair, who will introduce tonight's featured speaker.
All right, thanks. So first, I'll give you a little update on some upcoming speakers. Let's see, next month in June, we're going to have Bruce Ruggieri, who is a NASA JPL Solar System Ambassador. He's going to be telling us about the Europa Clipper mission. In July, we're going to have one of our returning champions, Bart Freed. I don't remember what his topic is offhand, but it will be about an old telescope. In August, we're going to have Don McCallernan, who's in the audience tonight. He's going to be telling us about some of his adventures in radio astronomy. And of course, in September, we have our outdoor meeting at Fort Washington State Park. Rest of the year is TVA so far. We will hear a little bit more. All right, so it gives me great pleasure to introduce this evening's speaker, which is Dr. Dave Chuss from Villanova University. So Dave actually started, he received his BS in physics at Villanova University, a place where popes have actually gone. After that, he did his master's at Penn State University and then his PhD at Northwestern University. That was followed by some time working at NASA's Goddard Space Flight Center before he came back to Villanova University, again, a place where popes have gone. And currently he's professor of physics and also the chair of the physics department, which makes him my boss. So Dave's research interests are in astronomical polarimetry, so using polarization of electromagnetic waves, including light, microwaves, and radio waves. He focuses on several different projects, including the cosmic microwave background, so the Big Bang cosmology, as well as, not connected there, as well as surveys of the galactic center of magnetic fields and material near the galactic center. So tonight he's going to be telling us about some of his work on that.
Maybe.
Maybe. Please join me in welcoming Dave Chuffs.
You want me to just share my screen to you?
Oh, but I'm just gonna end my screen share. Oh, you're not on the,
Do you want me to just share my screen to yours and then you can hear it projecting?
why are you not recognizing the projector? It's an adapter issue.
Should be.
Technical difficulties.
Yeah, I think we're okay. Do you want me to, why don't I share the screen and you can just keep projecting?
Oh, share it into Zoom?
Yeah.
Yeah, let's do that. That's for the easier way.
Have your,
Yeah, let's plug that back in.
I think I requested a screen share.
I don't know if you have to put it in again. There you go, you started screen sharing. Okay, let's bring that over here.
So if I play, I should be good.
Hey, that works.
All right, well, thank you all for having me and thanks Jeremy for inviting me tonight.
Oh, here's the
Oh, okay. I'm good.
that's on your computer.
Yeah, okay. So I'm going to talk to you a little bit about some of the research we've done in the past year or so. Specifically, there's some cool words up here, the magnetic field of the galactic center. And then I'm going to talk about results from the Stratospheric Observatory for Infrared Astronomy and what we can learn from infrared astronomy, specifically something called infrared polarimetry about magnetic fields in general. And then, of course, what can we learn about the galactic center? Now, our galactic center, the center of our Milky Way, what I'm talking about here is about the central 50 to 100 parsecs. So right around the supermassive black hole. It's an interesting region for a couple of reasons. Out of all of the interstellar medium throughout the Milky Way, there's much more matter in the galactic center. It's denser, I should say. There's higher velocities, and there is tangible evidence for dynamically important magnetic fields. Now, I have a background in here that kind of shows some of that, but I'm going to get into a little bit more detail a little bit later and try to convince you that that's interesting. The other reason why we want to study our own galactic center is that there's lots of interesting things happening in centers of galaxies everywhere else. We think outside of our Milky Way, there's quasars, there's other active galactic nuclei, Seyfert galaxies, all these different things where we think the central black hole in galaxies is really important for seeing these really bright objects out there in the universe. But we can't see them nearly as well as we can see our galactic center, right? Our galactic center is only about 24,000 light years away, 8 kiloparsecs or so. And so in addition to just really wanting to understand what our own galactic center is doing, because we're curious people, right? It also gives us an insight, a much up close and personal insight to what's happening in galactic centers in general, what's driving the dynamics of galaxies. And of course, galaxies are interesting because they're the places where stars exist, and stars are places that can host planets, and planets are, of course, places where we think life can exist here. So just to give you some context, I said I have these words, the Stratospheric Observatory for Infrared Astronomy here. What that is if you think about telescopes in maybe a different way here than is typically thought of, this is SOFIA, the Stratospheric Observatory for Infrared Astronomy. It's a NASA mission that's been that was a collaboration with the German space agency DLR. And basically, there's a Hubble-sized Cassegrain telescope in the side of this modified 747. This thing flies up to altitudes of about 45,000 feet and allows us to get a much better look at the sky than we can from the ground. And this is really important for the wavelengths we're looking at. They're not optical wavelengths where you do have pretty good views from the ground. It turns out in the far infrared, you almost have zero. And I'll go into more details on how that works later. This was fortunate enough to run for 12 years. I think it was prematurely canceled in 2020, but 2022, we can talk a little bit more about that later. It's a fun experiment to be part of. Actually helped commission the instrument that we're using on SOFIA, that we used on SOFIA for these big maps we've made. And I got a chance to fly in this several times as we were commissioning and then taking the data. So it was kind of a nice, I've got some photos of that a little bit later on in the talk. So our project that we use this instrument for is called Fireplace, the Far Infrared Polarimetric Large Area CMZ Exploration. It took us almost as long to come up with the acronym as it did to analyze the data. So I'll pause here so you can all appreciate the acronym. As Jeremy mentioned, I did come from NASA, so acronyms are really important, especially something like this. That's a compound acronym where one of the letters in the acronym is actually another acronym. This is the Central Molecular Zone, or CMZ here, and that refers to that central 50 or 100 parsecs there. So this data, we proposed this for NASA. It is classified as a legacy survey, which means the idea there was we were charged with taking data that would be useful not just for a single scientific question, but perhaps for the broader community. And what we did here is we covered about the central 1.5 degrees of the Milky Way. That is that central 150 parsecs or so, at 20 arc seconds resolution, at a wavelength of 214 microns. So about a quarter of a millimeter was our observing frequency. That's in what maybe the other folks would call the terahertz part of the spectrum. We call it far infrared in astronomy. And this was actually a technical challenge because 1.5 degrees is much, much bigger than the size of our camera. Our camera footprint on the sky is about 4 by 6 arc minutes or so. So we had to do some pretty clever, complex things to try to make this map. What I'm going to talk about over the next maybe 45 minutes or so is a series of papers that two of my postdocs, Natalie Butterfield and Dylan Perret, have led over the past few years that involve analyzing these data and then doing some science with it. So hopefully by the end of the talk, I'll convince you that we learned something new in this data set, in addition to kind of taking what I think is kind of a neat new picture of our center of our galaxy here. So this is just kind of a shout out to the team that we work with here. All the blue folks, the folks in blue here are either people that are currently at Villanova or have been at Villanova through some of this process. And then we work with a group of folks outside at a whole bunch of different other institutions across the country. All right, so first of all, I want to just explain everything that happened ever. So essentially, and I want to talk a little bit about how we do astronomy, and this is something that you all know, but I think it's helpful to kind of talk about the type of science that astronomy is, right? So basically, we have the history of the universe here. Time goes from left to right. And the outline of this trumpet-like horn here represents the size of the universe and the scale factor of the universe as the universe grows. So 13.8 billion years ago, everything started with a big bang. We may have had a brief period of inflation for the first fraction of a second. We have a series of phase transitions here where we go eventually produce the cosmic microwave background. We have the dark ages where the universe is homogeneous and not much is going on, right? But we're slowly assembling structure through gravitational interactions. And then then everything turns on to make us be able to do astronomy. We have the first stars showing up at about 500 million years or so. And this makes everything possible, right? Once we start forming stars, we can churn all that hydrogen into heavier elements that create dust and then planets, and they assemble into galaxies, and we can potentially have a second generation of stars, a third generation of stars. We have the elements in the periodic table we need to form us. So this becomes part of our own origin story. And then of course, all this evolution of galaxies and cosmic chemistry that happens over that next 13 billion years or so is what we're particularly interested in. This is where all these quasars and secret galaxies and all that kind of stuff happen. Now, we don't do any experiments in astronomy. We let the universe do those experiments for us, right? Light gets emitted from some event through some physical process. It gets absorbed, it gets scattered, it gets other things happen to it, it gets redshifted, all these things happen to it. And then we get to collect the light that happens to collide with our tiny little telescope, which is a tiny fraction of the light that's ever been produced in the universe, but it's enough to give us a handle on these, trying to understand what these cosmic experiments are doing. And there's several ways that which we do these things, right? One of them we call imaging, right? And really what imaging is from a physics standpoint is measuring the distribution of the directions of photon momentum. How much light is coming from that direction versus that direction versus that direction versus that direction. Most people would just say taking a picture. but we call it imaging. We talk about that as being the directions of photon momentum because light is the ambassador of information for us astronomers. We also then can talk about spectroscopy, right? Spectroscopy meaning what is the distribution of photon energy across the spectrum? And we can use this tool in a lot of different ways, right? We can look for signatures of particular elements. We can look for those chemical transitions between that we then identify elements, identify abundances of elements. We can tell whether those elements are cold or hot relative to their background. We can combine these two and do color imaging or spectral imaging. But both of these techniques, just assume that light is a scalar wave, right? That light doesn't have any kind of physics to it other than the fact that it's a wave, any kind of electromagnetic physics to it. We can add to that one other property of light that can tell us things about the universe, and that is polarization. Light is actually an electromagnetic wave, right? It oscillates in oscillating electric and magnetic fields. We call the predominant direction of the electric field of that light the polarization of light. And we kind of, by convention, we say it's the electric part, because most of atomic or molecular light interactions actually take place because of the electric field rather than the magnetic field. There's some interesting reasons for that, but I won't go into them now. And so if you have some kind of an anisotropy, some physical processes can pick out one polarization relative to the other. So light can oscillate up and down or left and right. And one of the maybe most common things we do technologically is to develop sunglasses that take advantage of this. Right? If I have unpolarized light from the sun reflecting off the surface of a pond, sorry, my pond is very clear today in this particular view. The polarization that is parallel to that surface will reflect much more than the polarization that's perpendicular to that surface. So sunglass manufacturers know this, and they basically make their polarized sunglasses such that it rejects this polarization more than it accepts this polarization. And basically that eliminates glare, right? Because of this anisotropy and polarization, you get this phenomenon of glare, but you can also develop your detector to distinguish between those two things and utilize it in a way that you can gain information. So here's kind of a picture, a real life picture of that. We're looking at a pond and we're seeing a lot of haze from basically the oblique reflections off the front of the surface, but those are polarized. So if I put on a pair of polarized sunglasses, I can eliminate that polarization and see the polarization that's reflecting off the bottom of the pond, and I can see through the water. We do the same thing with astronomy. We can detect the polarization of the light coming from events in our galaxy, for example. And this is the main technique we're using in Fireplace to say something about magnetic fields. It turns out magnetic fields provide a similar anisotropy that allows us to measure the direction of the magnetic field throughout the interstellar medium. So again, just anisotropy is just the fact that physical conditions are different depending on which direction the light is polarized. So what I'm going to talk about just before getting into showing you all the data, I'm going to basically show that polarization can reveal magnetic field structures in the dust phase in the interstellar medium. We have these little tiny dust particles, less than a micron in size, that are filling our interstellar medium. And it turns out these dust particles can interact with the magnetic field in such a way as to give us some indication. The first thing we have to know is something about how these little dust grains aligned. We have to assume that there's a good fraction of those dust grains that aren't spherically symmetric, that maybe they're little footballs or something, right? And they're spinning because they're colliding with each other, they're spinning around. They're also absorbing angular momentum from the radiation field around them. They're spinning faster and faster. They tend to want to spin about their axis of greatest moment of inertia. It's the least energy state for the constant angular momentum. So if they're footballs, they're not spinning like a spiral pass, they're spinning end over end like a kicked football. When they do that, they actually generate a little magnetic moment. And that magnetic moment is in the presence of our ambient magnetic field that's threaded through our interstellar medium, which is these thin blue lines here. And that causes a torque on these things, and they tend to start to align with the magnetic field. So what we end up with is a bunch of these little footballs that are that are spinning end over end, but they're predominantly aligned such that their spin axis is aligned with the magnetic fields. So if you think about these things sitting in space, this is what it looks like. These tiny little 0.1 micron-ish dust grains in space, and these are idealized. They're probably a lot uglier than that in reality, but this is the thing that Adobe Illustrator could draw. They're spinning, they have their moments of their magnetic moments aligned with the magnetic field. So basically there's a big anisotropy that's perpendicular versus parallel to that magnetic field. And so there's two ways that you can get polarization from that. If I put some unpolarized starlight behind that field, well, the polarization, the red polarization is parallel to those guys, gets absorbed more than the blue one does, and you end up with a polarized signal that's parallel to the magnetic field. So that's in the optical. If I have an optical, a bright star behind this polarizing screen, then I see polarization by extinction, and it's parallel to the magnetic field direction. Well, that relies on needing to know where a star is. So that can be useful, but it can be inconvenient because they're not stars behind every piece of dust you want to measure the magnetic field from. But if you go to longer wavelengths, these grains are cold. They're like 20 to 50 Kelvin or something like that. But if you go to the far infrared, they're glowing at those wavelengths. So you can actually see emission. And the emission is actually predominantly polarized in a direction that's parallel to the dust grains or perpendicular to the magnetic field direction. So this is the topic that we're going to spend most of the rest of the talk on, the fact that these dust grains align with the magnetic fields in the interstellar medium, and the polarized emission is perpendicular to the direction of the magnetic fields. So just to give you a sense for what we're talking about here, most of the history of astronomy has been done up here in the red through violet part of the spectrum. We have our near infrared, which is kind of our 1 to 5 microns. Then you come out here to 5 to 40 microns, would be called our mid infrared. What we care about here is the far infrared. You can see the spectra of dust, the characteristic spectrum of dust in the interstellar medium peaks around that far infrared. It's about 100 microns, terahertz kind of range here, a few terahertz. We can also see it out to the submillimeter. That's kind of 0.5 millimeter to 800 microns or so. And it sort of still appears in the microwave millimeter part of the dust of the electromagnetic spectrum, but we really want to focus on this here. That's really important because that's where our dust is the brightest. And then magnetic fields are also a challenge. Historically, magnetic fields have been difficult to measure and to understand really because of measurements, because of difficulty in getting good measurements of magnetic fields and using different techniques. They've also been difficult because the theory is more complicated. If you're trying to write down a theory where you're talking about how clouds of gas and dust collapse, and then you try to throw in a magnetic field in that and all the effects the magnetic field have on it, that becomes more complicated and more difficult to suss out. This picture is changing. We're getting bigger and better data sets. We're also getting better and better computer models. So we're starting to kind of understand this, and these two things are meeting in what I hope for over the next few years is a really exciting time for magnetic fields in our interstellar medium. So just a real quick tutorial on some of the finer points of magnetohydrodynamics. If you have magnetic fields threading some kind of matter that's ionized enough to be conductive, so you can think of it as a conductive fluid. The particles are fairly free to move along the field lines, but as they move across the field lines, they drag the field lines with them. When you compress the field lines want to push back. So there's this effect of the matter on the fields, and then there's a equal reactionary effect of the fields back on the matter again. And so a really simple picture of thinking about this is if I have a cloud of gas that wants to collapse into some stars, right? A big, maybe tens of parsecs cloud that wants to collapse down into some stars, and it's got a magnetic field flooding through it. Well, the right-hand picture shows that you can pretty easily collapse in the direction along the lines here. But if you try to collapse in the other direction, the fields pinch and push back. So you get the cloud shape affected by the fact that it's got a magnetic field. It doesn't symmetrically collapse to form stars. It collapses in this sort of pancakey shape. And we see this a lot in our galaxy when we look at the polarization of, say, Orion. We see this kind of hourglassy shape of the magnetic field in the Orion Nebula, for example, the cool dust in the Orion Nebula. All right, so I hope I've convinced you at this point that we can use polarization measurements in the far infrared to tell which direction the magnetic fields are in molecular clouds and dust clouds and in our interstellar medium. And that that's an important thing to do. So what we're going to look at here is the central, did it show up? Is the central 1.5 degrees. So you can kind of see it. There's a little box there, hoping that you can kind of see it as it blows up here. So this is our central 1.5 degrees. This is our central molecular zone. You can see that this is a kind of a nicely special part of our galaxy. There's a lot of stuff going on here. Again, this is a region that's 150 parsecs across. This is a mid-infrared image. So what we're seeing here is a lot of hot dust, some stars here and there. And you can see these crazy big features. Some of it basically forming this flattened disk, but it's. So I should also point out the fact that the black hole is kind of like right there. Now we can look at multi-wavelength imaging is really important in astronomy. The different wavelengths throughout the spectral range, radio astronomy, X-ray, optical, infrared, all give you a different view over different physical processes. They're sensitive to different things that are going on. So if we look at the radio, this looks kind of crazy different. This is the radio image of the galactic center. This is the Meerkat 1.28 gigahertz mosaic from an interferometer in South Africa. And you can see there are some features that sort of were the same, right? These thermal features here, these arc-like features show up both in radio where you have hot electrons swirling around, releasing radio waves, or just thermal glow. They're probably heating dust local to that region and they're glowing in the thermal part of the spectrum as well. But there is a lot of differences. The biggest one is that you see all these really weird structures that you see nowhere else in the galaxy, these what we call non-thermal filaments. And they're the technical emission mechanism for those is synchrotron. We've got relativistic electrons spiraling around these magnetic fields, emitting radiation across the low microwave part of the spectrum, the radio part of the spectrum here. So this is really the motivation for why we want to study magnetic fields. There are clearly magnetic fields in the galactic center that don't appear anywhere, don't manifest themselves like this anywhere else in the galaxy. Most of these features are very perpendicular to the plane of the galaxy, which is this way. So this is kind of the motivating feature for people asking the question, well, how important is that magnetic field in our galactic center? And then by extension, is that doing something in quasars and AGN and stuff like that out in the universe at large? Luckily, we can help here because this is the dust in the galactic center, and there's two phases of dust here. There's a cool dust, which is this orange component, and it's kind of this. If you follow my laser beam here, it's sort of a twisted ring type feature. And then there's a hotter dust that kind of corresponds with that mid-infrared data that we showed before. This blue stuff here. That dust is certainly worth measuring in polarization. Because now we can measure now we know what the magnetic field looks like in the hot ionized plasma, the radio picture we saw before. If we can measure the dust here, we can get a sense for how that magnetic field is maybe proportioned between the two phases of the galactic center, and maybe get some insight into the 3D structure of this part of the galaxy as well. So there's a couple questions we want to answer here. We'd really like to know what the strength of this field is. That's a tough question because we can't just walk out there and take a magnetometer to it. We'd like to know what the global field geometry is, how the field in the hot gas may relate to the field in the cool gas. We'd like to know what the sources of these relativistic electrons. There's got to be something energetic happening that's injecting relativistic electrons into these tubes of flux. And then finally, what's the importance of the field on dynamical processes in the galactic center? All right. So we're just going to take one more look at this here, and then we'll move on. Okay. So we want to ask the question, we said we wanted to look in the far infrared, which is kind of the peaks of, I put 3 dust spectrum here from, say we have 20 Kelvin dust up through 100 Kelvin dust. The problem we have from the ground is that the opacity of the atmosphere lets us do absolutely no observing in the far infrared. So the gray line here tells us how opaque the atmosphere is. And of course, in the optical, we're nice and clear. There's a few things in the infrared we can do. If we go out to the radio, we can look in the sky. There's a few gaps here that you can see on the highest mountains if you want to. but the peaks of these spectra are really, really opaque to water vapor in the atmosphere. So the solution to this is, of course, you go to places like the South Pole. This is actually where this whole thing started. I was a thesis student in about the year 2000 or so, working at the South Pole on this little telescope. The South Pole is about 9,000 feet altitude. It's a little drier than most places on the Earth, so it ends up being a little bit better than its 9,000 feet would indicate. This is my thesis instrument. We built a 9-pixel camera to observe the large scale magnetic fields in the galactic center. So this is out in the submillimeter part of the spectrum. And we measured this. We found across the galactic center, now it's tilted up rather than flat. We're in equatorial coordinates here. You can see an early picture of these threaded filaments here, these non-thermal filaments, and you can see our magnetic field measurements are these blue with yellow outlines. And I think we got about 20 measurements across the galactic center at about with a resolution of about 6 arc minutes or something like that. But we found that one of the striking things we found in these early measurements was that our field was not at all perpendicular to the plane. It's actually quite parallel to the plane, right? We've got these interesting dilemma now. So why is the field in the dust perpendicular to the field in the hot gas? We also looked on finer scales using a telescope on Mauna Kea called the Caltech Submillimeter Observatory, which is not there anymore. And we found that on these sort of 20 arc second scales here, the field actually is much more complicated than this simple parallel to the plane. It actually follows a lot of the features that we see in this case in the radio image. So again, we kind of face another dilemma. This doesn't all fit together at this point. Same part. The pink data here are our South Pole data. This group actually used the other polarimetric technique where you look at background stars to figure out what the magnetic field is. And they also found a parallel field, although they see hints of a perpendicular field if you go high and low here. So the story kind of gets thicker. Plot gets thicker, I guess I should say. More recent data sets, we're talking jump ahead 20 years here. We're still looking at this stuff. These are also pretty coarse resolution instruments. Pilot was a balloon-based experiment from Europe. They measured this field that's pretty uniform across our galactic center. The galactic center here is this little compartment here, right? And ACTPOL is a cosmic microwave background experiment at longer wavelengths, sees a very similar thing. They see these very uniform field structures that kind of tilt at about an angle of 20 degrees in this direction here. So so there's two possibilities that connect a perpendicular field in one phase with a toroidal field or a parallel field in the other one. So this was first proposed in the 80s and kind of keeps coming back at us. So if you have an initially vertical field here and you have, remember, the field is sort of frozen into the matter, right? If I stretch the matter, of course, the field pushes back, but it can also stretch the field out, right? It's kind of like hairs in Play-Doh. If I have hairs stuck in Play-Doh and I twist the Play-Doh, the hairs bend with it. Hairs don't bend back as much as magnetic fields do that. So what you would get here is if you had a dense region that was basically differentially rotating with respect to whatever this is pinned to in the high latitudes, you can get the stretching of an initially vertical field into a horizontal field. And you would actually observe that the field goes into the board in this case, or into the sky here, and out of the sky here, and out of the sky here, and into the sky here. It's a sort of checkerboard thing. And this paper in 2011 found that to be the case. You can actually use Faraday rotation measures in the radio to determine what the direction of the field is along the line of sight. So it's another parallel technique here. And they did find evidence that this may be happening. So that was kind of an interesting thing. Although there's also another model where you basically have some arbitrary field in the dense matter, and winds and supernova and all that kind of stuff can blow the field into a vertical configuration off the plane. So those are the two kind of paradigms we're dealing with at this point. So we come back to Sophia. So Sophia, we were able to propose this survey. This is the instrument we use. This is HAWK Plus. We use the 214 micron channel, which has just about a 20 arc-second resolution. When I first got to Villanova, one of the first things I worked on was trying to commission this. When I was at Goddard, the Goddard team built the detectors for this, worked with some people at JPL. Some of my students and postdocs got a chance to ride on the observatory with us, and we calibrated it and got it ready for the community to use. We also decided to do our own science with it. Just this is a good time for a break to just look at some cool pictures of what it's like to observe on a 747. These things have a lot of room when you take the seats out, turns out. So if you ever have to fly in a 747, definitely take the seats out. You won't get in trouble at all. So we're looking towards the back of the plane here. You can see the Naismith mount of the telescope is actually right, this blue thing back here. This is where the mission director sits, this is where the mission director sits, right here. The telescope operators are up here. This is before the flight. Everyone's kind of just like sitting around saying hi. It was kind of neat. We had to take safety courses to be allowed to fly on the plane. We had to learn all the ways of getting out of 747, whatever angle it lands at, which was kind of an interesting bit of information to have. But it was fun. It's really fun to fly on this thing. If we got to work our way back in the cabin here, this is the telescope operators, and you can see we're much closer to the instrument here. This is the Hawk Plus instrument. The instrument team is just sitting over here. Look, they have an oscilloscope right here. Just to make sure, I guess. If we go all the way back to the back, we have the $12 million instrument mounted to the Naismith mount of the telescope, the electronics racked to read out all of these superconducting detectors that are in this thing. And it's a liquid helium cooled system because we have to, in the far infrared, the energy of the photons is really low. The detector temperatures have to be really low in order for us to be able to have the sensitivity we need to see things. And one of the important things about a liquid cooled helium system is you always need the helium to evaporate. If it's not, you're going to get an ice plug, and an ice plug leads to overpressure and possible explosions. And you don't want to do that when you're in a plane. You don't want to do that anywhere, but planes are particularly bad. So we had this very sophisticated outgassing detection system, which is this trash bag that we tied on the top of the cryostat here. It worked. I don't know how the FAA. Anyway, we won't ask.
Don't say the word explosion on a plane.
That's fair. So this is our science. This is where the scientists sit. It's sort of at the side of the table. There's a big monitor up here so that the pilots can come out every once in a while and see what's going on in the instrument. This was one of our my first students at Villanova, who's now a postdoc at Harvard. He was responsible with getting the data, doing the simple analysis, and throwing it up on the screen so everyone can see what we did in real time. Just a real rough kind of cut of it. But that was pretty fun because this was the night we actually observed part of the central part of it right around the black hole, the central 5 parsecs or so. Okay, let's see. All right, back to the science here. So that was that. So this is the dust in the galactic center. We had that 2-color image. I had these two things before superposed on each other. This is the cool dust. This is about 250 micron emission here, so 1/4 millimeter. This is warmer dust. This is closer to the mid-infrared, not quite. But you can see the distribution of cool dust versus warm dust in the galactic center is quite different. If you look closely, you can see all these little vectors here. These represent the magnetic field measurements. These all represent magnetic field measurements, and these as well. This is all we knew about before we did Fireplace. This is basically years and years of building instruments to take them up to the tops of mountains and measure, waiting for the top 10% of the weather. Most of the time it's too much water vapor, even at Mauna Kea in Hawaii or on the South Pole. This is all we knew for the fine scale structure. But we realized that Sophia had incredible sensitivity compared to these places. So we were kind of thinking we could get a lot of this. So if you look at what we plan to do, the problem is our detector is this big on the sky. This is about 1,000 pixel camera of superconducting detectors. And so we had to make a map of this whole thing. So we did this and I won't go into too many details, but it is kind of interesting to the planning part of this was fun. So we did these stripes where we would scan the detector across the sky in this stripe, and we move it over a little bit and do it again. We'd have a lot of overlap, so that way, as the sky is changing temperature and opacity through the flight, we can just constantly keep calibrating. That's a complicated algorithm, but it was one that we had available. And then we go the other way in case that it mattered that we were going in this direction. We wanted to symmetrize it by going back again. And we did that on 18 fields across the galactic center. And then we just tried a bunch of different, we played with the parameters of the reduction software. And what we ended up with was a, so keep an eye on the top map here. What we ended up with was a much more filled in map of the galactic center. So now we have about, instead of about maybe several hundred measurements of the magnetic field, we have about 64,000 measurements of the magnetic field of the galactic center. The white line was actually our predicted sensitivity, and if I can, it looks better on my screen, I swear. But basically, if we filled this region with magnetic field measurements. So we were really happy with the result of this. We still think we can mine the data for more significant detections in this area here. But this was the end result map. Now, another way to look at this is through something we call line integral contours. So here we basically have these squiggly structures here, these streamlines that map the magnetic field. One of my undergraduate students was responsible for picking the color scheme of this map. This is a 3-color map that superposes the radio in yellow, the cool dust in cyan, and the warm dust in magenta. And the squiggly lines over top. And I do have this picture up here. I have posters of this for anyone who wants them. And if I run out, I can certainly mail you them. But you'll be able to see it a lot more close up on that. So this was the end result of that first experiment. And you can see it a little bit better now. You can see the streamlines here. And you see the New York Times ran this last about a year ago. We got a map in some Scientific American last summer. It appeared in the print issue. That was kind of fun. Went to the airport in North Carolina, and like the map was there. Space.com and Forbes also picked this up, which was kind of good. Mostly because we had a really good PR person at Villanova who was just kind of a master at kind of getting this in front of people. But again, you can see all the different little correlations between the field direction and the geometry of what the underlying dust and gas is doing here. So every time I have this on my screensaver, or my background at work on my computer, and it distracts me a lot. I'm supposed to be doing something with, I don't know, department chairs or stuff. And I'm like, wait, but I didn't see that before. And I kind of like think about it for a while. So it's a nice distraction. So I'm going to go through maybe a little bit of the science of this here. We've got, I've superposed this with all the other measurements at the Galactic Center. Since then, there's been a few more measurements from ground-based experiments. Apologies for this not being clear. It's just that there are a lot of measurements. So let me, this one's nice because we can kind of look at the global field here, and then we have some blow-ups here, which are a little bit clearer. So remember those large-scale arc-minute resolution maps that we had? Those are represented by these little directions. The red and the yellow are just the two different maps, what we call the pillow and the aft. And what we did was we kind of looked at, all right, what did the large scale stuff say relative to what Fireplace said right underneath it? And you can see these different regions show some significant disagreement. This one maybe not as much. They're kind of mostly aligned, but the Fireplace vectors here, the Fireplace measurements of the magnetic field sort of follow the little bean shape of this thing called the brick. It's clearly being bent by something. We think maybe there's shock going on here, but clearly the large scale structure is not seeing that as much, right? Same thing with this structure called the ring. The ring is, I'll show this a little bit later. The ring has this like azimuthal magnetic field around it, but this thing is just sort of straight across. So what we've really learned about this is that when you're making these measurements, you're really measuring everything from here all the way through the telescope beam to wherever it past the galaxy, really, right? So what we think is going on here is that these large scale things are actually picking up stuff in maybe the central, a much more uniform field in the central kiloparsec of the galaxy, whereas our Fireplace data actually zeroes in on the structures that are local to the central molecular zone in the center of the Milky Way. The other big takeaway here is if we just do a histogram on where the angles lie on Fireplace, right? We're thinking back to, is the field perpendicular or is it parallel to the galactic plane? We find that the answer is it's both. There's a bimodal distribution, some of which is nicely aligned with that large scale field from the from the Pilo and the large scale stuff. The other one is perpendicular to that. So these are vertical vectors, they're vertical magnetic fields. These are parallel magnetic fields. So there is this dual distribution. So something about the small scale structure is connecting with both the outer kiloparsec field, the parallel field in the kiloparsec, and that inner field in the plasma. So though it's complicated, it looks like we actually have found a connection between those two fields in this fine scale structure at the cloud level. This is a kind of a nice plot that showed up in our paper kind of halfway through the referee process. Basically, here we took all of the measurements that were mostly vertical and colored them in white, and the mostly horizontal ones we colored in red, just so you could see where the two different distributions are in the sky. We're looking for systematics. This doesn't really necessarily, nothing really shouts out here. But it was a nice way to kind of think of, it's one way to test what was going on here, which I thought was a clever lesson for if you make the right picture, you can kind of sometimes get the physics out of it. Sometimes it's if you write down the right equation, I guess. But the other thing we looked at was the comparison of the direction of the magnetic field to the individual cloud structures. Rather than saying just perpendicular and parallel to the galaxy, let's actually look at which way the clouds are stretched at every point in the sky, and compare that to what the magnetic field is doing in that direction. Here we actually found something else that was interesting, right? 0 degrees here, that's the difference of the two angles. 0 degrees refers to the fact that the cloud is parallel to the field structure, and 90 plus or minus 90 means that they're perpendicular. So most of the vectors actually follow the cloud structure. So the magnetic field is clearly being sheared in the dust. It's being stretched out in the direction with the clouds as they're sheared, whereas they're orbiting the supermassive black hole. This is just sort of a nice slide to say that this doesn't happen in the disk of the galaxy. It turns out that in the disk of the galaxy, the magnetic field configurations tend to be more perpendicular to the cloud structures because they're collapsing. Because in that case, you're looking at structures that are collapsing along the magnetic field. We also did the same test with the non-thermal filaments. We looked at the magnetic field direction in the dust versus the magnetic field in the NTFs. We found the opposite was true. That basically the dust measurements at the non-thermal filaments are perpendicular to the non-thermal filaments. So that was a little bit, that's still sort of an outstanding mystery there. So the wrap up for the global magnetic field is that the field is generally parallel to cloud shapes. The field is generally parallel to the galactic center at locations of the NTFs, but there still are vertical components in the field. They're just not systematically at the location of the NTFs, which indicates that maybe there is a pervasive part of the field that is perpendicular. Sorry about that. We also were able to put a rough upper limit on the field strength of the galactic center magnetic field, which is a few milligauss. Not a particularly constraining measurement, but we did it just for good measure. Just a few kind of a tour of some of the local clouds real quick here. How much time do I have left anyway?
10, 15 minutes.
Okay, yeah, that's great. Okay, so here's that brick again. And here you can see that the magnetic field here is very much shaped by the structure of the cloud. And this is nice check because a few other instruments have also measured it. And you can see all these vectors are pretty much in alignment. This is something called the three little pigs. These are three clouds that are more or less kinematically connected, that are basically right in the middle of the galactic center here. These clearly live in an ambient field that's perpendicular to the cloud morphology here. But you can see each cloud is bending the field a little bit differently, with the more massive clouds bending it more. This could represent three different stages of clouds that are coalescing to the point where they're actually being, there's a transition between them being pinned by the magnetic field and being pulled by the gravitational field. So you're seeing this evolution of shearing of the field in a very early stage here. Finally, there's this very interesting source that we found right at the edge of our survey. And it turns out we weren't targeting this at all. It turns out that there's a lot of people that have done galactic center surveys that weren't targeting this at all. But it turns out there's like 30 maps of this thing because of the fact that it's just sort of there when people take the map of the rest of it. And we found actually kind of this interesting thing. There's a ring of structure and the field just wraps around that ring of structure. So this was interpreted by Natalie Butterfield, who now works at NRAO in Charlottesville, as a compression event. Basically, you have a wind from maybe an old supernova blowing the field out into this ring-like pattern, compressing it. And actually, we did find that the field seems to strengthen along the central ridge of this structure here. All right, so the last little bit of the talk, what I want to do is I want to dig into some of the, we actually made some measurements that weren't part of fireplace, but they're at the higher frequency, the 53 microns, shorter wavelength. So they're about 5 arc seconds, and there are two particularly interesting sources in the galactic center. One is called the sickle, and one is called the circumnuclear disk, which is right around the black hole. So I think it's worth seeing those before wrapping up here. We're also kind of really thinking about what the production mechanism is for these relativistic electrons that are causing this phenomenon of non-thermal filaments. So you could imagine that you have a magnetic field, it wraps around itself, and it wraps around itself so much that it reconnects and releases all of its energy into the surroundings, right? There could also be compact sources, correlated supernova activity, past activity of Sagittarius II, or all some, none of the above. I think I've covered everything and been not specific at all here, right? All right, so what I want to show you next is the sickle molecular cloud. So we have the big radial arc here, the most prominent of the non-thermal filaments. There's a yellow cloud that's sitting right on the edge of that thing. Right there. Okay, so I'm going to zoom in on that. So this is an image of radio data showing that filament and showing the edge of this cloud, which is lit up with thermal radiation, actually non-thermal radiation. And then these are our vectors that we measured. This is our magnetic field direction that we measured with Hawk Plus. And you can see, again, this perpendicular superposition of these two fields seems almost non-physical because, well, they have to be not at the same location in space, right? You can't cross fields like that. There's a big star cluster here called the quintuplet. This quintuplet cluster is basically radiating this molecular cloud. We're only seeing the tip of the edge of the molecular cloud here. Actually, when we show the far infrared emission, we'll see that the cloud is actually a little bigger than that. This is just the irradiated front from these radiated edge of this from the quintuplet cluster. There's the main ridge that's getting kind of hit sort of straight on here. And then there's this like little pillars that are being formed because there's some instabilities where some of the parts are being held up more than others, and they're forming these little fingers. So here's another image of that with just the magnetic field vectors on here. The outlines are the far infrared flux, and then of course we have the same radio image underneath here. So I'm going to zoom in two parts of this here. You can see one of the amazing things about this is that this is one of the highest polarizations ever measured at 20% right here. It's really high polarization. So I want to zoom in on these pillars here. So you can see that one of the interesting things about these crazy little finger structures is that the magnetic field follows them out, right? So the magnetic field may be the thing that's providing the supports that's actually shaping these features in this particular region. The other thing to notice is that stuff is happening right at the site of one of these non-thermal filaments. So we're zoomed into the point where we might be seeing, if these are folding over, if the field is folding over at these points and providing some support, but then in the end, it's actually north, south, south, north, right? So those two things cancel out, the magnetic field goes away, blasts a whole bunch of energy into heat, energizing a bunch of electrons. Well, that could be a source for lighting this thing up, right? It's probably no coincidence that this thing is laying right on top of here with some enhancements right on these bright filamentary structures here. All right, there's one more piece I want to show because I think this is neat too. You're seeing another filamentary structure coming right through the cloud. There's an enhancement in the flux of in the far infrared back here, and you're seeing kind of a start of a bend right here, right? Most of this is pretty parallel, but this could be a start of one of those little those little finger features here, just in a really early stage. I'm going to talk about. I won't talk about that for now. So the last thing I want to talk about is the region right around the supermassive black hole. So this is the supermassive black hole is about right there, about 4 million solar masses, and it's driving the kinematics of the central region here. this is hot gas and dust that's surrounding that. And you can see the magnetic field is sort of sheared out in this sort of double spiral here. Let me show it to you here. This is some nice work that one of my former postdocs did on estimating the magnetic field. It basically, there's a shearing going along here, a shearing going along here, and a shearing going along here. And he basically tried to estimate the magnetic field strength as this feature just along each one of these clouds. So this was kind of a nice technique. He actually developed about 4 pages of math to do this, and then analyzed the data according with this math. It was kind of neat. So that's kind of what I wanted to show on this. The other thing about this is that these are 2 wavelengths of SOFIA. This is our fireplace data. Underneath it is the 53 micron data. So again, we're seeing superposed data, 2 different wavelengths that show different magnetic fields. Again, I think the answer here is that the high resolution data is really measuring what's going on at these clouds themselves, whereas this is another layer of magnetic field that's in front or behind the central 5 parsec region there. Just a look to the future. These are kind of what we can expect. So our SOFIA Hawk band right here is at 214 microns. This is where those Pelot data sit as well. We can look forward to the ALMA telescope, the Atacama Large Millimeter Array. It's a series of, I think, 48 10-meter dishes in the Atacama Desert that are capable of sub-arcsecond capability. So if you really want to look at the cores and figure out what the cores of things are doing, it has polarization capability, which is great. ALMA is a nice tool that I think will be very useful in the next few years. We're also currently proposing, there's a mission in NASA in a phase A study right now called PRIMA, which is going to have 4 polarimetric bands from space. It's going to be a cool telescope. So it's going to be, so if PRIMA actually flies and measures all these things, the sensitivity of PRIMA will be more of an increase than the difference between those 100 vectors we saw from the ground and the 64,000 vectors we saw sky. Basically, if you go to space and you can cool your telescope, you're just unlimited. You can measure almost the entire sky, which is kind of really quite cool. So I think I will leave it there. I'll leave these up here for you to read, and I'll take questions. And I'll also just mention that, again, we have these nice posters of this. I do have rubber bands too, if anyone wants to roll them up, take them home. Thank you very much for your attention. I hope you have fun with it.
Thanks. Any questions? Gotta be careful here.
Okay, this was absolutely fascinating, first of all, and I just wanted to ask, there was a lot of talk about dust, and I did want to know if dust extinction had any relevance to this, and if you had to overcome that at all in your research.
That's a great question. So dust extinction happens in the optical, because in the optical, dust is really opaque. As you go to longer wavelengths, the light is actually longer than the dust, so it doesn't interact as much. But it's the same dust that extincts in the optical that we're looking at in emission here. It's that same dust that we're looking at that's glowing at 214 microns that at 500 nanometers would just be blocking everything out to the galactic center. Good question. Yeah.
Other questions? Yes.
So unlike the airplane, I assume while you're moving, I mean, there's turbulence, right? How would you deal with that? And it seems like it adds another layer of complexity to like track the sky while you're moving at like 500 miles an hour.
That's actually a great question. I'm glad you brought it up because I forgot to mention something about that. So when you're moving in the plane, the telescope is extremely well gyro stabilized. So when you hit some turbulence and you're standing, say, at the coffee machine in Sophia, right? The plane actually shakes a lot. The telescope doesn't. Telescope is dead reckoned on the sky, unless it's like really extreme. Basically, the plane shakes around the telescope. So you can feel yourself kind of moving around. The telescope is just keeps pointing. It's really well engineered. The Germans did a really nice job with it. They're the ones who designed it.
Yes, my question.
Oh, good.
So when you're on the plane, it looks like the telescope is shaking,
Yeah,
doesn't it?
absolutely. But you also feel like you're moving. So
Yeah, you're gonna sing like,
yeah. You also have to carry oxygen, portable oxygen with you if you get out of your seat, because decompression at that altitude is, I guess, a possibility. I guess they say.
It is a plane with a hole in it.
It is, yes, that's right.
Other questions?
Well, I'm happy to stick,
I was just wondering whether the heat from the jet engines was a factor.
No, the heat from the jet engines is lower, and then they have to look above a certain. It's geometrically done so that the jet engines are on the bottoms of the wings, and then we're looking kind of the top of the airplane when we point. So good question though. Yeah, absolutely. Yeah, it was a non-trivial effort to design the modifications to the 747 to get it to aerodynamically fly with that door open, first of all, and then to make sure all the other things that happen don't ruin your observations. Yeah.
Other questions?
So I'm happy to stick. Go.
Is where the telescope is, that physically isolated from where all you guys were sitting rather than, it's open?
Yeah, it's a hermetic seal
Okay.
right at the Naismith bearing. Yeah.
About non-trivial things. Here's a trivial thing. Why do you speak in parsecs?
Oh, why? Light years? I think it's, certainly we're beyond the point at which a parallax arcsecond means anything at 24,000, which is probably the point of your question, right? Just habit, I think. There's so much that's ingrained in from the early days of astronomy still, like magnitudes and the Johnson filter stuff. It's sort of like the standards that fell into place in the right way when this was all kind of developing as a culture. I think that's most of it. Yeah.
What's the difference between professional and amateur astronomers, right? Professionals use parsecs and the amateurs know how to find stuff.
That's fair.
All right, anything else? All right, let's thank Dave for a great talk.
Wow, that is art. Beautiful. Thank you. Okay, everybody, that concludes our meeting today. Thanks everybody for coming. Yes, check out the posters which are available. There's quite a pile of them here. I think there should be enough for everybody. Take a look at the books that are left on the table. Just a donation of $1 is all you need. Let Jeremy know if you would be able or like to attend the memorial service for Lou Barbarizis. And I guess that's all. We'll see you here in a month.
Oh, can I?
Thanks, Jim.
That,
Appreciate it.
that was really good.
Thank you.
That was an incredible presentation.
Oh, thank you, Sylvie.
I just wanted to comment.
Oh, yeah, of
Wow,
course.
that was incredible.
Let me
Are
take
the-
your brain, setting
Yes.
up a 2-meter disc.
Oh my goodness, I'd love one.
What do you?
Thank you. These are beautiful. Yeah.
Oh, okay. No, I mean, not sure.
Grab them quickly. I didn't count them.
Take a look at the example of the merch too. Forgot that.
Yeah, I'm trying to.
Oh, of course.